We are back to again this module 1, this last part of this module, that is review concept of fluid mechanics and thermodynamics. So, I think I have in the previous two lectures I have clarified the some of the important topics of fluid mechanics and thermodynamics, and in fact these two topics, that is fluid mechanics and thermodynamics, is very vast, but to the best possible extent I just tried to give some brief introductions that are essential for this course, that is modern compressible flow, and I have talked about those topics of interest that are related to some sense to the compressible flow. So, if you have to recall the learning components from this module, then you must ask yourself that whether you know this or not on these broad topics. That is, you should by this time you should be able to define the definition of a fluid, and in particular if it is a gas, because the shear stress is absent here. Also we talked about fluid flow, its classifications. We introduced the concept of continuum into the fluid motion, and with that relations there are Lagrangian and Eulerian descriptions. Then we introduced the concept of total derivatives, and acceleration and stress, these are the two important topics, and for these fluid particles, if you want to find out its acceleration and its stress, and if we want to express it in terms of space as well as time, then the field concept is introduced. So, we call this as a acceleration and stress field. Then we introduced the concept of how the forces are experienced by the fluid, and in particular the forces are expressed as a normalized component and tangential components. Then after having discussing all these things, we try to give some insight to the governing equations, that is mass, momentum, energy equations for a fluid flow, and in particular we did it for an inviscid analysis, and these equations can be represented as a integral as well as differential form. In fact, we tried to find out that how this integral and differential form of equations for an inviscid compressible flow will be beneficial for our application. Now, these are mostly on fluid part, and coming back to thermodynamic part, because why I am saying thermodynamic part, because this is equally important, because since the properties, many thermodynamic properties of the gas, many thermodynamic properties of the gas and fluid, they are related in many sense. In fact, to have this more clear, we can say the first law of energy equations and first law of thermodynamics and energy equation of the fluids, they are almost same. Then we have this for this thermodynamic, after this thermodynamic properties, we also talked about ideal gas equations, laws of thermodynamics, and then the important part is the compressibility, in particular for a gas. This is one of the vital part. We are concluding this in this thing, so that in the next module we will be able to start from this as a beginning, in the sense that this is the essentially the most important part of this course. Now, in this course, although there are many numerous problems that are available, but I will try to give some insight of some standard problems how just to clear certain concepts. So, this particular problem, that is first problem, we are talking about a Eulerian vector field. So, normally when we say vector field, it is represented by three components I, j and k, that is in orthogonal coordinates. If I write x, y, z, and these unit vectors are I cap, j cap and k cap, and we can say the velocity components u, v and w. And here for this, and if this at any point in the space is defined by this vector field, then we can say here u will be t, v will be x z and w would be minus twice t. Okay. Now, we wanted to have this acceleration of this fluid particle. So, acceleration, for acceleration we can recall this as derivative of this velocity vector dv by dt, and this is nothing but dou v by dou t plus dou u by dou x plus v vector dou v vector by dou x vector, v dou v vector by dou y, and w plus w dou v vector by dou z. Okay. Now, from this equation one can directly calculate, we know u, we know v and we know w, and we want to find out these components. So, from this equation we can rewrite dv vector by dt, dou v vector by dou t, that means partial derivative with respect to t both. So, when you do this, the only where the t term is present we have to return this, that is I cap minus twice k, and dou v vector by dou x vector. So, we can write, so the first component there is no x, only there is a second component, that is x. So, dou v by dou x will be z j cap, dou v vector by dou y. So, there is no y in any of the term, so we can put it 0. Dou v vector by dou z. So, if you look at z here, only middle term has z component, so we can write that is x j cap. Okay. So, this is how we can write. So, after finding these terms, we can simplify this as I cap minus twice k cap plus u I can put as t, dv vector by dx I can put z j cap, v I can put as x z, dv by dy is 0. So, this part will be, there will be nothing here, and w we can put minus twice t, dv by dz we can say x j cap. Now, from here we can simply write, we can separate it out I, j and k. So, from these two terms, this and this, we can write 1 minus t z, this is j cap, this is j cap. So, we say I cap minus plus these two term contains j cap. So, plus I can write t z minus twice x t j cap plus, sorry, this will be minus twice k cap. So, this is 0. So, we can write this acceleration vector as this. So, I cap plus t whole bracket t z minus twice x t j cap minus twice k cap. So, from this velocity vector, by using these derivatives one can find out this acceleration vector. Okay. The next problem that talks about a use of this talks about use of what I can say a Bernoulli's equation. Or in other words we can rewrite as steady flow energy equation that involves head loss. So, when there is no head loss, this steady flow equation turns out to be Bernoulli's equations. So, what the problem talks about, that we want to pump a gasoline in a pipe of diameter 100 mm and the distance I want to go in an elevation of 150 meter. So, the fluid is gasoline and what needs to be calculated? We have to calculate the frictional head and velocity head. So, this frictional head, why there is a frictional head? Because this is being this gasoline is being carried in a long pipe of this diameter, and as and when it flows there will be loss in the pipe, and that loss is accounted as a head loss HF. Now, to calculate this, one simplest expression of steady flow energy equation can be used, which is, that means we can put as I as inlet, E as exit. So, P I by rho g plus V I square by twice g plus Z I is equal to P 2 sorry P I P exit by rho g plus V exit by 2 g plus Z E plus HF. This HF will be added in this part because this is at the exit. So, as and flow ends here, so we will have this head loss. So, this has to be calculated. So, one thing we can say, since it is a constant diameter pipe and it is a gasoline, flow is incompressible, and when you say flow is incompressible and area does not change. So, we can say V I will be V E, and that is nothing but volume flow rate by area. So, volume flow rate we can find out because we know the mass. So, since we know mass and we know that is 15 kg per second, and for density of gasoline, that we can find out from the any book, that is about 680 kg per meter cube. So, once we know mass and density, we can find out volume. So, once we know volume, we know area, pi by 4 d square, d is your 100 mm, that is 0.1 meter square. So, after putting it, we can find out this term v square by 2 h g, that is nothing but velocity head. So, this term, after putting all these expressions so all these values, we can calculate this v square by 2g to be about 0.4 meter. Okay. That is what we require the velocity head. Now, to calculate this friction head, we have to use this equation, and in fact, in this equation the velocity head remains same for the both sides. So, what we can do is here, and you can have Z d minus Z I would be 150 meter, and this P I minus P E by rho g would be 25 minus 1 is atmosphere 101,325 Newton per meter square, rho is 680 into 9.81. So, this we know, velocity head remains same, Z d minus Z I, Z d minus Z I also know. So, from this equation we can calculate this H f to be about 215 meter. So, head loss would be about 215 meter. So, this example gives you that how to use this steady flow energy equation in a given problem, and in this problem the fluid is gasoline and in general it is incompressible. And next important problem, we are going to talk about a centrifugal compressor of 0.5 meter diameter is used to compress hydrogen at 15 degree centigrade and 1 bar. Calculate the maximum allowable rotational speed to avoid the compressibility effect. So, here the solution we should start from the fact that we should find out that how, because we are asked to calculate the rotational speed omega. Okay. So, the omega and velocity of this can be related as omega and v, that is linear velocity. Can be related by the fact that v is, you can write r times omega. Okay. So, this will be r is d by 2, that is 1 by 2 into 0.5 into omega. So, this is will be in meter per second. But what it is asking that to avoid the compressibility effect at the blade tip, then we have to calculate what is the sonic velocity. Sonic velocity is defined by square root of gamma r t. Now, here this your medium is hydrogen. So, for H 2 we say gamma to be again 1.4, but r is something different, that from data sheet we can find out it is 4124 joule per kg Kelvin. So, by putting this, we know gamma r t and temperature is about 15 degree centigrade. So, we can say 1.4 into 4124 into temperature is 273 plus 15 square root, and this number we can find it out to be 1289 meter per second. So, in order to have the velocity at the impeller tip, that is half 1 by 2 point into 0.5 into omega, if this speed does not have to account the compressibility effect, then we must satisfy these conditions that your V should be less than or equal to 0.3 of A. That means, when your Mach number is less than equal to 0.3, we say that is incompressible flow is treated to be incompressible. That means, hydrogen the medium the flow the flow will be treated to be incompressible, so that there will not be any compressibility between the blade tip. So, in the blade tip your velocity is v and your speed of sound is 129 per meter per second. In order to have this compressibility effect to be neglected, your v should be less than or equal to 0.3 times A. So, if you put it, we can turn out to be half into 0.5 into omega should be less than equal to 0.3 into 1294. So, this will land of omega to be about 1553 radian per second once you put this number, or you can say omega is about 1481830 rpm. So, this number is nothing but the rotational speed, that is about 14,830 rpm. So, this example talks about that when a centrifugal compressor is operated in a compressible medium, then you can see this rotational speed of this number about 14,830 rpm. So, this number is essentially very high, and normally all the aircrafts they operate at this rotational speeds. In fact, all conventional aircrafts the rotational speeds will be of this number in the range of 15,000 rpm. So, the next point again we bring here as the isothermal compressibility at a pressure of 0.4 bar. So, isothermal compressibility when you calculate, if you recall our analysis, we define a parameter called as bulk modulus, that is 1 EV, that is rho dP by d rho at constant t, and from this parameter we, if you put V is equal to 1 by rho, we define a term tau t, that is compressibility 1 by rho d rho by dP, and when you put rho in terms of V, then we are going to get in terms of density in terms of specific volume, that will be minus 1 by V dV by dP at constant t. So, this is the term which is used for isothermal compressibility and represented as a function of pressure and density or specific volume and pressure. So, here what you say dV by dP, when I say dV by dP in a total in a differential form, ordinary differential form, but when I express them as a dou V by dou P at constant t, then we are saying that we are defining this compressibility in for a isothermal medium, that is keeping temperature constant. Okay. So, having said this, we can say tau t is tau t comes in these expressions. But what we can say is that if you say air which is at 0.4 bar pressure, that means we can say 0.4 into 101,325 Newton per meter square. Okay. So, this is the data given. So, we need to calculate the isothermal conductivity at a pressure at, let us see, for an ideal gas. So, for an ideal gas we can write P is equal to rho R T. Okay. So, when I say rho R T, or we can simply write P v is equal to R T. Okay. So, from this we can write P is equal to R T by V. So, we require dV by dP. So, it is better that you express V in terms of P. Okay, V will be RT by P. So, this will be dV by dP at constant temperature will be equal to minus 1 by P square into RT. Okay. So, we can write tau T would be minus 1 by V. So, V will be minus P by RT. V will be this V will be P by RT. So, it is minus P by RT into this is minus 1 by P square into RT. So, RT gets cancelled, P will get cancelled. So, tau T will get minus 1 by minus will be plus, so 1 by P. So, by putting this we can write 1 by 0.4 into 101,325. So, this tau T will give the value of 2.46 into 10 to the power minus 5 meter square per Newton. So, this expression says that the isothermal compressibility for any gas at a pressure of 0.4 bar, which is 2.46 into 10 to the power minus 5 meter square per Newton. The next problem we are going to discuss about a situation where we have a pressure vessel that has a volume of 12 meter cube is used to store high pressure air at 20 bar and 25 degree centigrades. So, we want to calculate the internal energy of the gas that is stored in the vessel, that is first part. Second part is that if the gas is to be heated at 350 degree centigrade, then you have to find out the entropy change. So, this is a very classical thermodynamic problems where we need to calculate the one of the property, that is internal energy. So, internal energy nothing but it is, we can say it is Cv times T total energy, and we second part we are going to calculate about the entropy. So, let us solve the problem. So, basically we have a container here, in that volume has 12 meter cube, it has pressure 20 bar, temperature is 25 degree centigrades. So, it is a closed container, and when and we also in this container we are also going to add heat, so that this final temperature becomes 350 degree centigrade. So, let us do part by part. In the first part, so when I say this entire container, so I must calculate the what is the mass of the gas that is in the container. We have given the volume. So, we have given volume as 12 meter cube, P as 20 bar and T as 25 degree centigrade, that is 293 Kelvin. So, mass we can calculate, that is volume times density. So, how do you calculate density? Density we can calculate rho is equal to P by RT, and since this is air, so you can say R is 287 joule per kg Kelvin. So, from this we can find out rho, for which 20 bar into 101,325, 287 is the R, temperature is 293. So, this will be rho would be about 23.7 kg per meter cube. So, we know volume, we know rho, then we can find out mass. So, this will be 284.4 kg. So, once we know the mass, we can find out internal energy. So, total internal energy U internal is mass times small u internal, that is m into this internal energy is nothing but Cv times T. So, for air we can write either you write this way or you can write Cv m times Cv will be R by gamma minus 1 into T. Okay. So, Cv is R by gamma minus 1 into T. So, when you put all the numbers which are known to us, then we know m, we know R, we know T, we know gamma, then we can find out this total internal energy of the entire mass is about 60.8 megajoule. So, this part it is now clear, internal energy. Now, if the gas is heated to 350 degree centigrades, then what is the change in the entropy? So, you have to recall entropy equation, that is S2 minus S1 is Cp ln T2 by T1 minus R ln P2 by P1. So, since it is a constant volume process, okay, so we can say P2 by P1 is also equal to T2 by T1. So, we know T2, that is 350 degree centigrade. So, it will be 350 plus 273 divided by T1 would be, T1 is 25 plus 273. So, we know temperature ratio, we know pressure ratio, we know Cp, Cp will be gamma R by gamma minus 1. So, we know Cp, we know R. So, we can find out S2 minus S1 as 529 joule per kg Kelvin. So, remember this is per unit mass, but we have total mass about 284. So, total entropy change, that is S2 minus S1 would be mass times small s2 minus small s1. So, this number would be about 150 kilojoule per kg Kelvin. So, this is the total entropy change for a for the mass 284.4 kg. So, this entire problem talks about all types of thermodynamic properties, how this is going to be calculated. So, likewise there are many such problems that can arise in this particular module. So, it is suggested that the candidate should refer some standard problems to brush up the knowledge of fluid mechanics and thermodynamic fundamental aspects. So, with this I conclude this module 1. Thank you for your attention.